Alright, hey guys. Quick video on just the basics of how circuits work. It's really hard for learning just through a textbook, even an interactive one with simulations and stuff. I know it can be tricky, so I'm just going to go over kind of some basics about circuits really quickly with the video. I'll do some more of these. I feel like these might be helpful. I don't know. We're all still sort of learning how to do this, so. After I do this one, you guys have a series and parallel assignment to do. I'll do a video on how to analyze series and parallel circuits and the differences and all that stuff. This might be a little cluttered, and from where the camera is, you might not be able to see some of it, but when I post this video, I'll also post the PDF version of exactly what I have here, so you'll be able to follow along on what I have. I'll also post other notes and stuff, so like you see there's some symbols and all that'll be on some other notes and PDFs as well. I wanted to put as much as I could on one thing because I feel like the more I post, the more overwhelming it is for you guys, so I just wanted to keep it as compact as I could. So anyway, a circuit is a closed conducting loop from positive to negative of a voltage source. So the two things you need for a circuit is you need a voltage source, which could be a battery, it could be your wall outlet, it could be a generator. There are lots of things that can provide voltage. And you need a closed loop of conductor, usually a wire, right? Copper makes a good conductor. Silver is actually the best conductor. The reason we don't wire our houses with silver, though, is because that would be an expensive house. But we just need a closed loop from positive to negative. 99% of the time, we actually have something connected, like a light bulb. We technically don't need it. It's called, if we don't have anything connected there, it's called a short circuit, which is still a circuit, but not a very useful one. You're going to see these symbols a lot, so I put these on the side here. There are also plenty of other sources online. You can look at just circuit diagram symbols. These are called circuit diagrams. Circuit diagrams keeps everything at like right angles. If you're drawing a circuit, instead of drawing wires that might overlap each other or trying to actually draw a battery, it's a lot easier and more consistent and easier for people to figure out if you draw the symbols and draw it as a diagram. This is much easier than trying to draw where the wires actually go in a room or a house or on a table, whatever. So these are circuit diagrams. These are the circuit diagram symbols. And these are the names for a bunch of components or things you can actually put into a circuit. There are more. We'll talk about a fuse, which protects the circuit. We'll talk about some other things. This is what you would draw for if it's a light bulb. You could draw a speaker for a speaker. I mean, there are lots of symbols. We'll talk about just these for right now. A battery and a resistor are the two most, and a wire are the three most important ones. A battery is two parallel lines that are uneven in length. It means something different if they're the same length. A resistor is just this squiggle. A resistor is anything that basically takes the energy of the battery. So a light bulb counts as a resistor, a speaker counts as a resistor, a fan, a heater, a motor, anything that uses the electricity is a resistor. Now there are also just resistors whose job is to limit the current. If you have a device that can only take a certain amount of current, but you have a battery that can push more than that, you put a resistor in so you get just the right amount of current. So a resistor could be anything from a light bulb or something that uses the energy to just something that's meant to limit the current, because more resistance means less current. We'll talk about that later. So these are things you can actually wire into a circuit called components. These, current, voltage, resistance, are three vocab words for things you can measure in a circuit. Voltage is the energy that each coulomb of charge has. We don't really need to talk about coulombs from here on out. But it's the energy that we can think about it as the energy that each electron has. The current is the actual flow of charge or the flow of electrons in a wire or in a circuit. It's the amount of electrons per second that are passing by a certain spot in the circuit. So current, voltage, and then resistance. Resistance depends on how thick wires are. You'll notice that a light bulb can be, before LEDs, was a really, 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 really skinny, long wire. That's providing resistance. Just like a really long, skinny tunnel, if you have to crawl through it, it takes a while to get through. So resistance depends on the physical properties of the material. You guys probably saw that in your last CK12 assignment if you did it. But it's the opposition to flow. If you get something that's different temperatures can lead to different resistances. There's more molecules bumping into each other. Temperature, length, the area, cross-sectional area of the wire, all of these will determine something's resistance. So you can't change a circuit. Well, you can change it. We'll talk about that later. But anyway, current, voltage, resistance. The third one that we'll talk about later is power. That's how much energy per second some device or something uses, or how much energy per second that the battery supplies. And that's also a really useful thing to measure. It's stamped right onto all of the components that we'll use in our house. Like a microwave is 1,000 watts. A light bulb is 60 watts, right? Power is an important, but we'll talk about that later. All right, some facts about circuits. These are often misconceptions, so we'll look at these for a little bit. Electrons are everywhere. They're in everything. Everything's made up of protons, neutrons, and electrons, so they're everywhere. They have negative charge. So if I say the charges or a certain amount of charge flows through, we're talking about electrons. Protons can't move around in everyday materials like metal and circuits like this. You can get protons to move around in a lab or like potentially lightning or something like that, but inside materials, electrons are the only things moving. So if I say like the charge moves around, I'm talking about the electrons. Electrons have negative charge, and they're the things that can be moving. They can be moving because they're on the outside of each atom. Protons are stuck in the nucleus, so they're stuck there. They can't move. If you ever hear yourself writing like protons move or the positives move around, then you're doing something wrong, right? Protons can't move around. If we're talking about even a conductor, even any material, protons can't move. So electrons are the charges. They're in everything. They're already in all of the materials we use in a circuit, ready to start moving. Okay, a common misconception is that batteries provide charge. Batteries, this one's down here, provide energy. They're going to sort of give that electron energy. Essentially, they do that by putting a big negative, right? Batteries have two sides, negative and positive. If you connect the negative side to the positive side, electrons don't want to be near the negative side. So just by connecting those up, you've given those electrons over there energy, and they want to flow towards the positive side. They're attracted to the positive side. So the batteries are giving those electrons that are already there. They're already sitting in the metal, like ready to move. They're giving them energy. These electrons, they're free to move in conductors. They can move wherever they want, essentially. Metal has a little resistance, but not much. Or wires, rather. And they move very slowly. This is another common misconception. If I turn this light switch off and turn it back on again, electrons do not rush from the light switch all the way to the light in that amount of time. What happens is, picture like a tube of tennis balls. You have a tube of tennis balls and it's full, right? Like one of those fresh cans of tennis balls, smell great, right? If you cut one end open and so it's 3 tennis balls in a tube, and now both ends are open, right? You cut the bottom off, take the top off, both ends are open. If I push a tennis ball, like add a 4th tennis ball into that tube of 3, and push it into one side, all of them start to move at the same time, and one comes out the other end. This one that I pushed into this end does not go all the way through really quickly and then come out the other end, right? It just pushes all of them over one. Same thing happens in the wall right here. All of this wiring is full of electrons, like tennis balls in a tube, ready to move. So if I flip on the light, that closes the loop, and they can all start moving over one spot. But they don't, the one that was right in front of the switch doesn't fly really quickly to the light. They all just start moving together. All of them start moving together. So that's a common misconception. People think electrons travel at almost the speed of light to get there. They don't. The electric field that's turned on does, which is why all of them can start moving at once, and even the electrons that are in the lights already can start moving. But electrons only move about this far in an hour. If I was sitting in this room for an hour, on average, the electron that was at the light switch, now they're all bouncing around in there, but on average, the electron that was here might only move to here in an hour. So that's, they actually move really slowly. Finally, when an electron finally gets to the light, it's in the light bulb. What happens is it bumps into lots of other atoms, molecules, right? There's a lot of heat and light that's what provides the resistance. The energy gets used up. That's what happened. The energy gets converted to the light. If it's heater, the energy gets converted to heat. If it's a speaker, the energy gets converted to motion energy, which gets converted to sound energy. But at no point does the electron get used up. This is just kind of pet peeves, which is why I want to go over these. We don't say that the electrons get used up in the light bulb. The energy does, and what happens is the electron might go in the light bulb with a bunch of energy, or at a high voltage, right, energy, and come out the other end of the battery at a low voltage or low energy. That's what voltage is. That difference between the energy that the electron had when it went into the light bulb and the energy that it has leaving, that's what voltage is. You may have seen on those simulations the analogy to water. Water, before it goes through a water wheel, is up high, has a high potential energy. It gets converted into kinetic energy, rotational energy. At the end, when the water's done going through the water wheel, it's at a low potential energy. Same thing with electrons. Not with height, but with electrical energy. So light bulbs use up the energy, but the electron never stops moving. Even when it has very little energy and it's already at the other side of the battery, it's at the positive terminal, it's where it wants to be, it doesn't have a lot of stored energy, it's still flowing through the circuit. So if we look at a circuit like this, the electrons continuously flow around the circuit. They don't get used up and leave at a light bulb or a heater. Energy gets used up, but not the actual electrons. The electrons will keep flowing and come back to the other side of the battery. We'll talk about series and parallel more in the next video. We already looked at, or you already looked at, hopefully, the relationship between current, which symbol is I, voltage, and resistance. Basically, the more voltage you have more push, and so you can get more current going through a resistor or a circuit. But if you have more resistance, this fraction gets smaller, and you have less current. More resistance, less current. That's why if I have this dimmer switch over here, right, I have a dimmer switch on the side of this. If I bring it down like this, I'm increasing the resistance, and the reason I can tell is because the light gets dimmer, which means the current is going down, which means this must be the high resistance. It's resisting the flow a lot more than this one is. All right. One thing you might see that's kind of confusing, but I don't know why they never changed this. If I was in charge of physics, I would change this, but the direction of current is the direction of, conventionally, I don't know why they do this. Again, if I was in charge, I would change this, but current direction is the direction a positive would go. Even though we know that electrons move around now, they used to think that positives moved around. When they actually learned that it was the negatives that moved around, instead of switching this, they just said current is the direction that a positive would go. It's super annoying. I think they do it just to spite physics teachers, but that's another thing that you might see. It doesn't really come into play in anything we do, but you might see it. So we'll talk about series and parallel in the next video. We'll also talk about power and energy a little bit more. later on. I hope these videos help. I felt like the Zooms weren't working, and I felt like I was hanging out to dry a little bit. So hopefully these help. I'll post this PDF, I'll post this video, and I'll post some more notes and stuff like that you can use. I don't want to post too much because I don't want to be overwhelming, but I also don't want to leave you hanging. So hopefully you like these. Hopefully I covered most of what will be helpful. And I'll see you later.